My name is Matt Billock. I'm a product manager with Backand, and today we're going to be discussing serverless function performance. I came up with the idea for this presentation while I was doing some performance testing on AWS Lambda a couple of months ago. I had done some analysis of our previous function calls. Backend has a hefty integration with AWS Lambda and a lot of production functionality that's built on Lambda. As a result, I wanted to get a feel for what Lambda looks like in a production environment. While I was doing that, I was hoping to express different aspects of serverless development, such as the cost it takes to spin up a function container and so on. And thus this presentation was born. So today we're going to try to take a look at the round-trip HTTP performance times of three major serverless function providers: Google Cloud Functions, AWS Lambda, and Microsoft Azure Functions. Here's a quick overview of our agenda. We're going to start by discussing what it takes to compare serverless function providers. It's unfortunately not simple because, as you can imagine, different products have different features. I know this is extremely advanced knowledge. Once we've gone through some of the caveats I have to keep in mind when comparing serverless functions, we'll then go through the process that I use and review some of the code. I wrote 3 Lambda functions, and I wrote a Ruby script that runs a performance test over a few days. After that, I want to give some warnings about the data. I don't claim to be a data science expert, and it's entirely possible that there are better ways to analyze the data than what I've done here. And if that's the case, if you see what I'm going through or what I presented and you have some suggestions, I'd love to hear them. Again, you can email me at matt@backand.com. Also, if you have any observations or questions, you can use the questions functionality in GoToWebinar or the chat functionality. I won't be addressing those as I move through the content, but after I finish the presentation, I'll be sure to address all the questions that I can find. In any case, once we've gone through all of those 4 items, we'll then look at the results, both subjective and objective, and give a brief overview of Backend at the end in case you're not familiar with what we have to offer. So comparing serverless functions, what we're really talking about when we're saying comparing serverless functions is that we're looking for differentiating factors. If you're doing serverless development, your choice is many times dictated by what drives the rest of your application's ecosystem. If you're built on top of AWS, for example, you're very likely going to be looking at AWS Lambda as your function provider. If you're built on top of Google Cloud, same thing, you're going to be using Google Cloud Functions, and again, with Microsoft, we'll be using Azure Functions. But it's important to recognize that these choices do have some impact on your application design. Specifically, the hot-cold nature of many serverless offerings results in potential delays in processing ability, especially if you have like dozens of functions composed into a single serverless application that can really impact your performance. So it's really good to be able to go into this with open eyes and get a feel for what you're preparing. So from that perspective, we're really looking at presenting this data in terms of finding these differentiating factors. What is it that sets Google Cloud Functions apart from AWS Lambda? What does Microsoft Azure Functions have to offer, and so on? So along those lines, we had to look for ways for things that we can compare. The first thought, obviously, is that let's compare the UI, but that is extremely subjective. Something that I find patently obvious, somebody else could be looking at and think it's in a foreign language. And similarly, something else that somebody finds extremely easy to use could be the most complex thing that I've ever used. So as a result, I'll present some conclusions on the user interface and the experience, but they're definitely not universal, and I highly recommend you not to try to restrict your choice based on the user interface. Along those lines, then, we start taking a look at more technical restrictions in terms of choosing serverless providers. The platform choices vary, but they're ultimately a non-issue. In short, all the providers support node.js and very popular languages. So, ultimately, when you're choosing a serverless function provider and you've made that choice, the choice of platform isn't necessarily going to be a major component of what you're trying to say. I mean, obviously, if you don't have any node.js knowledge and you're strong in Python, you're probably going to go with Python. But beyond that, the platform choice becomes largely a non-issue. So it's important to note those as a point of comparison, but I wouldn't base a decision off of those. Another thing to note when doing this kind of comparison is that, as you can expect, all of these providers keep a pretty tight seal on their hardware requirements and what kind of environments you run your functions in. You can get general data like operating system class, memory allocated, software versions, things like that, but you can't get full statistics. So from that perspective, doing an exact comparison between the hardware offerings is not really possible simply because it's not made available. So from that perspective, well, once we've eliminated everything else, the only thing that's really left that we can do to differentiate between these 3 competitors is compare similar functions running on each platform using similar source code. And that's what we ended up doing. So I'm going to walk through each of these service providers that we're testing, and then I'll go through a bit of the code and the process that I use to test these. So we're going to start with AWS Lambda. AWS Lambda, for lack of a better way to put it, is the elder statesman of the serverless realm. It was launched at reInvent in 2014, and in many ways, it kicks off what is currently known as the serverless trend. Prior to the launch of AWS Lambda, serverless was called Backend as a service or platform as a service, and it's just a general extension of software as a service technology. And AWS Lambda looked at what was going on. We had the growth of Docker at that time. It was allowing for containerization of applications, making scaling and deployment really easy. And Amazon basically looked at that and said, well, why can't we do that with functions? And that's what they've done, is they've taken the containerization approach and really scaled it up to web scale so that you can use it to run individual components as microservices, maybe call them pico services because they're not necessarily truly fully fledged web applications. AWS Lambda offers a number of triggers through AWS services, and they also offer an HTTP trigger through API gateway. I'll mention why I call out the HTTP triggers in each case in just a moment. And they have 4 supported platforms: Node.js, Python, Java, and C#. And also within each of these platforms, they have different supported versions. For example, they do Node 4 and Node 6, as well as the Node at the edge, which is a lower cost kind of Lambda alternative. The next one we're going to take a look at is Google Cloud Functions. It was launched quietly in alpha early in 2016, and then released to beta later that year. It leverages Google's internal infrastructure. I had a conversation with a developer advocate at Google who mentioned that it's using the same hardware that Google.com is running, so they definitely have the capability to run a web scale. Again, similar to AWS, it has triggers with all of the Google Cloud services, or a significant portion of them, as well as an HTTP trigger. And unfortunately, their platform choice is extremely restricted given the beta nature of the product. Similar to Henry Ford saying you can have any color you want as long as it's black in your car. You get Node.js and only Node.js when working with Google Cloud Functions. I'm sure this will change in the near future as Google continues to grow, but at the moment, that's really all you have to offer. The final contender in our serverless shootout is Microsoft Azure Functions. This was launched in March of 2016 with an official release last November. It ties in tightly with the Azure platform, as you can imagine, offering ties into the various Azure services or also over HTTP. It also has the widest support of execution platforms, with C#, F#, Node.js, obviously C# and F# given that it's Microsoft. Then you have Node.js, Python, PHP, but you also get the capability to run bash scripts, executables, and just, if you have these one-off utilities that you have to run on a periodic basis, maybe they're in a cron job now on a server that you're paying for, you can move them to a serverless function, potentially save a lot of headache. So now that we've reviewed each of the contenders in our serverless shootout, let's take a look at the process that I use to test this data. My goal all along is to keep the code simple and equivalent. The one thing that we're going to face very quickly is that each of these function providers, they have different return requirements in terms of what they respond to the user. So as such, we can't do an exact equivalency simply because it's not the exact same platform. But if we keep our functions fairly straightforward, then we can probably do the best we can do in allowing for a direct comparison by just minimizing the amount of time, the amount of things that we're handing off to, say Node.js in terms of processing. In this process, as I mentioned, or I haven't mentioned yet, but the reason I call it HTTP triggers is that I'm using the HTTP triggers exclusively. This entire performance system is geared off of it's geared off the premise that you want to compose multiple serverless functions into a web app. And from that perspective, it's the HTTP round trip time that's the most interesting. It's what's going to affect your application's performance most severely. Just a moment. Sorry, I've been practicing this webinar fairly frequently, so I've got a bit of a tickle in the throat. I'll be pausing to drink water every once in a while. So moving on, the process, I called each of these functions 10,000 times with random pauses of up to 20 minutes every 100 calls. The goal here is that I want to get a feel for what the average round trip time is, but I also needed to express this hot-cold functionality because you need to look at the worst case. The best case obviously is going to be there's always a machine ready and available to run my functions, but if your functions are intermittently run, say there's a long pause between them, there's a very good chance that the next time you call it, Google or Amazon or whomever needs to spin up a new instance that can then be used to execute your function. And there is time cost to having that done. So I wanted to get a real feel for what that is, so we can then extrapolate that into, say, what a web application would experience. So I'm designing the test using simple post requests. All of the body data is exactly the same. I send a simple JSON body with a message parameter that contains a message that says like hello serverless function or something like that. I don't have any warm up or warm down cycle, which you typically see that when you're doing like code performance testing and code profiling, and it's vital because it allows the cache to build on the processor. We don't really have that in terms of what we're doing here because we're going through so many systems and with an HTTP round trip. It could be argued that I could improve this by having a warm up, warm down, and discarding say the first 1,000 results from the last 1,000 just to make sure that I'm getting a true subset of data. I have some other techniques that I've used to kind of account for that in terms of excluding outliers, but we'll get to some of this later in the caveat section. After it's run its post request, it just outputs the script I wrote just outputs data to CSVs, and then you import that to other tools to provide some basic statistical analysis. So this test had two components. It had the serverless function code, and it had the test script. The test script's written in Ruby. We'll get to that in a moment. All of the serverless functions are written in node.js, and very quickly we ran into a problem in that we can't do a direct version comparison. Because each provider uses a different version of Node. AWS has Node 6.10.2, Google Cloud has 6.11.1, and Microsoft has version 6.5. AWS also offers Node 4 and an additional Node version, but I'm not too concerned about that. So there could be some variation in these results based on the fact that we're just using different node versions. All my code is doing is accepting a message parameter and responding with a simple message that concatenates a static string with the message that was received. So I don't feel like I'm running up against any potential walls in terms of the version, some major performances between Microsoft or between Node 6.5 and Node 6.10. If you disagree or if you want to discuss further about how this could impact the results, please send me an email, matt@backand.com. So the test script itself, I wrote it in Ruby just because that's a language I'm very comfortable with. It's a fairly minimal script. It sends 10,000 requests. It outputs all the data to separate text files for each providers. And I have it pause for 0 to 20 minutes between each 100 requests. As I mentioned, I'm looking to test the hotness versus coldness of the function. And you do see some of that through native execution, but I wanted to make sure that I had a couple of calls for each provider that I could guarantee would hit that cold state. And by pausing every 100 requests over 10,000, you're getting just about 100 pieces of data at minimum, which is what I was really looking for. I didn't use any special libraries. I wanted to absolutely minimize the potential confounding factors, so I just wrote everything in that HTTP library, which is built into Ruby. I use Ruby version 2.4.1. Here's an example of how I'm sending these HTTP requests. And I'll note that this code is exactly the same for every provider. It's just that the URL changes, and I believe I had to add an authentication header to one of the other function providers. I don't have my code at hand, but if you want, I can discuss this further with you later. All we're doing is we're creating the URI, we're constructing the HTTP request, then we're sending the HTTP post off to the provider. Then we return the request, and we output some data to the console for tracking. Now, there are ways this can be improved. I could, for example, move the URL HTTP request generation up to static content. But in a more traditional web application, you're not going to see that because things will be more variable. So I felt this was fairly indicative of the typical usage pattern you're going to see in a web application. Taking a look at how we measure the trip time, all you see here is that we're just we create our text file. We then run a loop 10,000 times where we record the start time using the Ruby time library. We send the function and get the response from AWS Lambda in this case. Then we record the finish time. We then do it twice more, once for Google and once for Microsoft. And then once we've gathered all the times, we output all this data to a file, just recording the run number and the difference in time. Now, this could have some potential issues in terms of how accurate Ruby's timing library is. In my experience, it's been good enough in terms of giving you things you can use to produce conclusions. But maybe you have a difference of opinion there, and again, I'd be happy to discuss. You can see at the end here that we're doing a simple sleep for up to 1,200 seconds at every 100 requests. I have another timed argument where you can make it sleep every request, but as you can imagine, that could very quickly turn into very, very, very long running tests. I also have some very basic error handling code. My error handling code was written with the express intent of keeping the script running at all costs. So any error that's encountered, I output the error message to the console, but I don't record it anywhere. And that's something that I'll mention when we get to the caveats and ways to improve this analysis in the future. Speaking of those caveats, we have a couple of areas that we need to quantify. The first is our test environment. I'm using consumer cable internet, which is subject to, if you're not familiar with how a cable internet is generally structured, you have nodes that are connected to a central hub, and then from those nodes, you distribute the connection over coaxial to each of your subscribers. As a result, this means that you're subject to additional load on the node. I live in a residential area which has a bunch of other houses around here that are connected to the same node. If everybody gets home and starts browsing Netflix at the same time, it has the potential to overload. It has the potential to overload the connection, reduce my ping times, and reduce the round trip time. So it's something to take into account that I'm using consumer-grade internet through Comcast, which is of course well known for its quality and its customer service. But so the first thing you want to just recognize is that this isn't necessarily the best connection environment. I'm also running on a MacBook Pro and not using a dedicated server in a rack anywhere, which means that I have a general purpose machine doing performance testing for HTTP, which can somewhat conflate the results. And so it's just important to keep that in mind. And finally, I'm connecting over 5 gigahertz Wi-Fi, which I'm not sending a lot of data, so I don't feel it has a strong effect on the round trip times, but it does have an effect just simply due to low bandwidth. And it's also my my home local network, so I've got other traffic like my kids watching Netflix or my wife browsing the web. So that could also be a confounding factor. If we wanted to really effectively improve this test, we want to get a dedicated server connected to say a T1 line or somewhere on the internet backbone that has the minimum amount of headaches between starting on a machine and getting out to Amazon, Google, or Microsoft. Then on the serverless function side, we have a couple of additional caveats. The first one is that when you're using AWS Lambda, you have to use API Gateway if you're going to do HTTP triggers. And API Gateway does some additional work on top of handling the web request. It does some transformations on the input to get it in the appropriate format for Lambda, and then it can do additional manipulations on the output. This can add extra round trip time, but I don't really have any way to quantify it because aside from this, I don't have any real way to truly test round trip time outside of using the AWS SDK, and I'm not certain that's truly a fair comparison. So it's important to note that this could have slightly skewed the results in the favor of both Microsoft and Google. And if you're working with Amazon, I highly recommend you start looking at a way to build in native HTTP support, as both Google and Microsoft are very good about giving you HTTP triggers right away for your functions if you want them. Another thing to note, as I mentioned before, we have varying node.js versions. I don't think it's a major concern, but it's definitely something to point out. And if there was a way to compare the exact versions, I would absolutely love to hear it. Then the third thing is a little more obscure. So both Google and Amazon, when you create a new function, they allow you to specify the RAM size on the machine you're using. And at least in Amazon's case, I don't know about Google, if you specify a higher RAM size, you get more processing power dedicated to your functions as well. You're not given this capability in a very easy to find place in Microsoft. And I actually didn't find out where you could do it in Azure Functions until well after I completed the test. There's a configuration screen you can get to for your functions that lets you set the maximum memory. So basically what I'm saying is that both Google and AWS in this test were running on machines with 128 megabytes RAM. I have no idea how much RAM was allocated for my Azure Functions. And if I was to run this test again, I would definitely focus more on making sure that I had equivalency in machine architecture to the extent that we have it. And then finally, the final caveat for the serverless functions is that we have different return requirements between each platform. All of them are HTTP responses, but they all have different patterns that they use. For example, both Microsoft and Google offer you a request object or a response object that you populate with response code. You populate the body through a method call, and then you return that object to the Google system or Microsoft system, which translates that to the response that you received in the HTTP request. Amazon, on the other hand, wants you to respond with a JSON body that is then sent through a filter and API gateway, and then turns that into, into the response that you see. So these differences, though minor, they can have some effect on performance. But given that we're talking about fairly basic processing within the language, you're not doing anything too complex. I'm hopeful that it's not doing too much to skew the results. But if there was a way to get true equivalency there, that would be the best. But unfortunately, I don't have that. In any case, with those caveats out of the way, let's take a look at some of the results. First, I wanted to list some subjective results, having worked with all three platforms. Take these with a grain of salt. They're all based on my personal preference and my background. And as I mentioned before, what may be easy to me may be hard for you. What may be hard for you may be what may be easy for you may be very hard for me. So in my opinion, the best UI was Google Cloud Functions. I was up and running with a function that I could hit over the web in under 10 minutes, and it was just a breeze from start to finish. AWS and Microsoft it's just so much better experience on Google. It really surprised me how well that worked. In terms of most configurable, Microsoft's Azure Functions definitely have the most configuration options once you can figure out where to track them down. And that ties into my next point, which is that Microsoft Azure also had probably the most complex UI out of the three, with AWS Lambda being a close a close second. If you've never worked with Microsoft Azure before, the first time you log in, you're presented with a large blue screen and a hamburger menu on the left with no cues whatsoever, which is very, very poor UI design. I had no idea where to go once I've logged in, and it's definitely something that you should take into account if you're going to be working with a lot of, say, engineers who are newer to the serverless space or perhaps newer to Azure Functions. In terms of most complex configuration, that RASI goes to AWS Lambda, and this is entirely because of the use of API gateway. Both Google Cloud and Microsoft, once you get to the part where you're creating the functions, make it very easy to set up HTTP triggers for your functions. AWS makes you go through API gateway, and they also do this thing where they don't actually tell you that, by the way, you're using API gateway, so now you have additional return requirements in your function. You can't find that anywhere very easily in the documentation. I hunt down a forum post that told me about it. To give a comparison of what I'm talking about, I was able to get a function I was able to hit over HTTP on Google in under 5-10 minutes. In Microsoft, just due to the more complex UI, it took me maybe 15-20 minutes to have a function ready to go. At Amazon, I had the function itself written in under 10 minutes, but I wasn't able to hit it with an HTTP trigger for another hour and a half as I spent my time searching for those return requirements and why every time I call my function, it would say there was an internal server error rather than returning my data. So, just something to keep in mind. If you work with Amazon, I'd really recommend you revisit how you're using API gateway and give us maybe some more basic triggers we can use as a template before we're ready to start leveraging the full power of a tool as complex as API gateway. Because I know there's a lot of value there, but especially if I'm getting started and trying to evaluate products, I don't need that value. Finally, the final word is the most obscure logs, and that also goes to AWS. Microsoft is a close second here because their logs are fairly easy to access, so they don't have a lot of very useful data that you can pull out. Google is very good in terms of providing log data. I can pull usage data out very easily. I can export it all from one interface. I try to do the same thing from AWS, which uses CloudWatch to manage the logs, and that is it's an involved process. You have to take the CloudWatch logs, you export them to S3, and then you have to pull them from S3 down to your local machine. And when you pull them down, you notice that they do some kind of time division based on log data, and I believe it defaults to like a 24-hour division, which I'm sure is configurable somewhere. I just haven't looked for it. But in any case, if I run the test over 4 days, I have 4 separate folders that each contain 1/4 of my results, and I have to write another script that goes into these files, pulls out the data, and then can parse it. So, definitely some improvements to be gained on the logs, although given my use case is not typical, so there's probably good arguments to be made for why it is that way. With the subjective results out of the way, and again, please take those with a grain of salt. I need no offense; these are just my observations. Let's move on to the objective results. So here's a combined histograph of each of the runtimes for each of the functions. This simply took the time values that I obtained from my Ruby script and sorted them into buckets, automatic buckets based on the time that a function took to run. You can see Microsoft Azure Functions here in yellow, Google Cloud Functions in red, and AWS Lambda in blue. But in terms of process, I used a 5% outlier. So one of the things that we face here is that we're dealing with web requests. If a web request fails, say it times out, you're going to have a 30-second runtime. You compare this to the vast majority of functions which run in well under a second, usually less than under a quarter second. And if you simply take the data as is, you get a really long graph with a very small peak on the left side, very small peak on the right side, and absolutely nothing useful in the middle. So by putting in 5% outliers, I'm able to get some usable data, and I'm able to get a better look at what the performance was of your typical function. And taking a look at this graph, you can already draw some conclusions. We see a strong peak on the left side of the graph for Microsoft Azure, and you see that it maxed out. It has a highest incidence of about 110 milliseconds of round trip time to actually run your function. Then you can see a clear bimodal distribution for both for both Google Cloud and for AWS Lambda. We'll get into that more as we go through each of these providers. We're going to start with AWS Lambda. You can see here that AWS Lambda is clearly bimodal. You have a couple other minor humps. Let me pull up a pointer here so I can make some highlights. So if you're not familiar with the modality of the graph, that simply means it's got extra humps. Bimodal means 2 humps. And in this graph, you can see a major hump on the left, a major hump on the right. Then we have 2 smaller humps. So you can almost call this quadrimodal. I don't know necessarily what's up with these smaller humps. So it's entirely possible that I have some additional testing to do. But just based on this observation, just based on this data set alone, we can make a couple observations. Namely, we see very clearly the hot mode performance here. Sorry about that. we see very clearly the hot mode performance here at about 0.16 seconds for AWS Lambda, and then the cold mode performance at 0.26 seconds. So you've got a differential of about a tenth of a second in terms of spinning up the resources to run a Lambda function. Moving on, we're going to take a look at Google Cloud Functions, and it's the same kind of thing. You have a clear bimodal distribution and then a long tail. Something I found interesting about the Google data when compared to Amazon is that you have, let's take a look back at the Amazon data. You see here you have high peak, then you have low trough, then you have high peak, low trough. What that means is that your data is bimodal, but within those individual modes, it's very narrow. I mean, you're going to get performance that's predictably very, very close to either of those peaks at 0.16 or 0.26. With Google Cloud Functions, you can see a much higher trough, even though the peaks are closer together at 0.16 and 0.22. You've got a much higher trough, and that means that your results are going to be more distributed on this range between 0.16 and 0.22. So ultimately, you're going to, in a lot of ways, you're going to get more variance, but the variance is within a tighter range. So I guess it's kind of a wash when it comes to performance. The final element was Microsoft Azure Functions. And I found this graph very interesting. I was really hoping to test the bimodality of Azure as well, but I must not have hit their cache busting time effectively. Apparently 20 minutes isn't necessarily long enough to really generate the kind of data. So all of their calls happen in under 0.2 of a second, with the exception of a large stack at the end, and I'll get to that in a moment. But as a result, I don't see any bimodality, which means one of two things. It means either they're not bimodal, which would be amazing, and I'd love to hear how they architected it, or they are bimodal, and I just didn't exercise it effectively. So a repeat run of this test with more frequent or longer pauses might potentially expose that functionality. But you can see here that Azure has a peak right here at 0.1 of a second or so, and then it trails off very quickly with up to about 0.16, which is where the other two providers are running at. So now we're taking a look at the graphs. Let's take a look at the data itself. I've done some basic analysis. Here, first, I want to take a look at a success failure and the kind of metrics that come from there. As I mentioned, I wasn't doing a lot of error tracking, so a lot of this is just when something goes wrong, I don't have data on why it went wrong. So I had to find some interesting points of data. Given that all of these providers returned on average in less than a quarter second, I quickly came up with a metric of any call that took longer than a second. There's probably an aberration and something to note. And it's definitely an interesting data point to see how many of these calls, for example, took longer than a second when the average call is definitely far less than a second. And in that case, you have Google Cloud Functions has the lowest number of calls that took longer than a second to complete at 1.15%. AWS Lambda is far behind at 1.38%, but Microsoft Azure has had the highest, I guess, I don't want to call this an error rate, but rather the highest aberrant round trip time at 1.68%. Another thing of note here is that we're working with the web, and the web is by nature somewhat inexact, meaning calls can end for no real good reason and without much information about why. So I took a look at the overall count of calls that just did not complete, and as you can see here, there's definitely something weird going on with the Microsoft Azure Functions. Both Amazon Lambda and Google failed only once out of 10,000 calls and successfully completed 9,999. Microsoft Azure Functions, on the other hand, using the exact same code and the exact same pattern in the exact same environment, failed 388 times. And 3.9% is a fairly large error rate, something to take into account and make your decision. Now, it's entirely possible I'm doing something wrong either in Microsoft or in my test script. I doubt it because I'm keeping everything very basic just so I avoid this kind of situation. So it would be really interesting to do some additional research to find out why that error rate is so high with Microsoft. Moving on, I did some simple aggregate analysis using basic statistics. A quick caveat here is that I use all of these techniques are great, but they're all intended for uniform distributions. As we're dealing with two bimodal distributions and a long tail distribution, it may not be accurate, but I still find it provides you some general guidelines to guide your thinking when you're discussing the performance of these functions. So we'll start with the mathematic average or mean round trip time. For AWS Lambda, it was 0.243 seconds. Google Cloud was 0.25, and then Microsoft Azure came in the clear winner at 0.16 seconds, definitely the fastest of the three. Then we want to look at the median round trip time, which is going to be what was the exact middle, and that was again Microsoft Azure Functions coming out on top at 0.11, with AWS Lambda close behind at 0.2 of a second, and Google Cloud in a close third, losing 5 milliseconds to AWS Lambda at 0.218. And then we'll take a look at the mode, which is the most commonly occurring value. And at Microsoft Azure, that was 0.126, definitely still the fastest. AWS Lambda in a close second at 0.16 seconds, meaning that more often than not, you're hitting the hot case than the cold case with Lambda. And Google Cloud is at 0.233, meaning exactly the opposite. You're most likely hitting the cold case more often than the hot case. The final element is the standard deviation. Now, in a normal distribution, this can give you, if you have a piece of data, this can very quickly tell you what percentile or what quantile that data falls into. But in a bimodal or a long-tail distribution, it's not quite as useful. All it really does is help you get a general gauge for the spread of the data. From this perspective, both Google Cloud Functions is the winner in that all of the data is going to be within a certain range. You can fairly depend on that at 0.164. AWS Lambda is a bit behind that with more variance at 0.192, though in this case, as we saw in the graphs, the variance is actually a benefit for AWS Lambda because the times are a lot more predictable. Microsoft Azure, on the other hand, had a much larger standard deviation, mostly due to the long-tail nature. You had a set of results on the left, you had a set of on the far left that was significant, you had a set of results on the far right that was also significant, and that kind of screws with things a bit. But despite their fast runtime, it definitely had the highest variance in my testing. The final thing we're going to take a look at is the hotness and coldness of these serverless function providers. As I mentioned, Microsoft Azure showed very little, if any, bimodality, so we can't really say whether or not they're going hot-cold. So we have to then compare just what we have, which is Google Cloud and Amazon Lambda. And in both cases, they both responded very quickly, and they were well within the order of magnitude of each other, well within a margin of error of each other. Both of them had the same average for a hot run at about 0.16 seconds, and then Google had the slight edge on Amazon Lambda at 0.22 versus 0.26 seconds. The difference between the two is about 40 milliseconds, which if you extrapolate that, let's say you're building a complex web application and has 20 serverless calls, that equates to a potential maximum differential between the two of about a second per page load, which can be significant, and it's definitely something to keep in mind if you're doing a lot of kind of hardcore serverless communications. So I wanted to conclude the results portion of this presentation with some observations, just kind of to summarize what we just saw. As I mentioned, the shortest mean and the shortest median both go to Microsoft at 0.162 and 0.111 seconds, respectively. The most consistent performance was Google Cloud Functions, and I measured this through the standard deviation in terms of being predictable in terms of there. But then you have a couple of other things to look at. Namely the most long calls, which goes to Microsoft. They had 1.68% of their calls take over a second to return, and then the most errors, which was Microsoft again at 3.9%. Again, this definitely is telling me that we need to do more research in this area. And if you happen to have a framework that exercises this, I'd love to hear what you're doing. Finally, the fastest warm-up time in a hot-cold situation when comparing Lambda and Google is Google with 0.06 seconds. But there's not really that significant a difference. So I wouldn't necessarily say that this is something that should be a differentiating factor when choosing a cloud services platform. So now that we've gone through the results, let's take a look at some ways that we can improve the analysis. This is tied to our caveat section earlier. And these are just some thoughts that I had in terms of how I can create more consistent results. So the first thing we want to do is we want to increase the rest time and increase the interval, basically because I want to see more of that bimodal exercise. But the problem we're going to run into very quickly is that, ideally you'd want to pause for a random amount of time between each call, and because that would give us, the most realistic kind of function performance data, as it would be in a traditional web application that has people pinging it from all over the world. But that very quickly becomes a very long test. If I rest a maximum of 20 minutes, I do that for 10,000 calls. We're talking 200,000 minutes, which is, well, simply put, a long time. I just don't have the time to run that kind of hardware run that kind of test in a dedicated fashion. Another thing I'd like to do is to improve this test is to gather the error types and reasons. Right now I have an absence of data, but perhaps there was a 503 error where the service wasn't available, a 404 error for whatever reason, or just a simple timeout. And having data on what the calls were and being able to graph that would be very useful in terms of determining how critical those failures are to your usage pattern. And then, of course, there's the test environment concerns. Obviously, we want to use a dedicated machine with a dedicated internet connection that has a very large pipe, and maybe pulling a server on rack space or something, and doing it that way could produce different results. All right, so now that we've gone through the serverless functions, I want to tell you a bit about what Backend has to offer because they were so kind as to allow me to perform this kind of research and push forward the serverless community. So Backend is the serverless app development platform. What that means is, if you're not familiar with that, is in a traditional client-server application, for a lot of web applications, your server is actually very light. You do some basic CRUD work, you do some basic business logic on the side, and for the most part, all of your other work is just translating client-side calls to database calls. We've built an API that basically allows you to automate that. Using Backend, you can automate we'll manage your application's database. Every application gets an Amazon RDS instance. We also manage your security and authentication and give you a consistent API with which you can work in order to produce your application's results. We then provide a number of other features that you can use to replace server. One very cool feature is we do custom server-side code execution, either through inline JavaScript functions or using serverless functions like AWS Lambda. Then we provide some additional supporting features such as hosting options, logging analytics, and there's really a large list of features here. It turns out replacing a server isn't necessarily the easiest thing in the world. But while I'd love nothing more than to spend the next 8 hours discussing each of these features in detail, if you'd like to learn anything else about them, please don't hesitate to email me. All right, well, that's all I have. I want to thank you much for your time and for taking the time to learn about some serverless performance differences. Again, my name is Matt Billock. I'm a product manager at Backend. If you want to discuss these results further, feel free to ask a question using the questions feature in GoToWebinar or the chat feature. Otherwise, you can reach me at matt@backend.com, or you can check out what Backend has to offer at www.backend.com. Thanks a lot for your time. If you have any questions, please don't hesitate to ask them. I'll hang around for a couple more minutes in case anybody wants to ask. All right, we got one question from Christian Seifert. It says, did you make the test including a DB connection, SQL or NoSQL? I guess there'd be more real-world examples. Yeah, that's a great point. I did not because I was explicitly focused on the HTTP round trip time. Because a lot of times I really don't have a good reason why I didn't. Other than it just wasn't something I was really looking at. I was trying to minimize the confounding factors so I could get as close to an apples-to-apples comparison as is possible. Giving those. And it's definitely a great follow-up test. I mean, if you're interested, I can send you my script. You can modify it to do additional expressions so that you have more of a real-world performance. Just send me an email, matt@backend.com, and I'd love to have a discussion. All right, I'm not really seeing any other questions. So I'll just say I didn't get to your question. If you had a question that you didn't get a chance to ask, please don't hesitate to email me, Matt, M-A-T-T, @backend.com, or ping me on Twitter, Matt_Billock, or contact us at backend.com through Intercom or via our contact page. We would love to get in touch with you. Thanks a lot for your time. I really appreciate you attending. I hope you found this interesting. Have a great rest of your day.